Welcome to section 4.4. This is actually a really short section, having had 4.3 be really long. And so it gives you guys a little break. We're going to now talk about solutions, because what if your chemical is dissolved in water? There are always two parts of a solution. There is, and again, a solution is a homogeneous mixture. Okay, so we can always separate at least the parts of a mixture by a physical process. And that goes back to chapter 1. Now, it comprises two parts, the solute, and this is the this is the portion that is present in the least amount, the smaller amount, whereas the solvent is present in the larger amount. And so you could have, let's say, 50 gallons of water, H2O, and let's say we only have 1 gallon of milk that we've poured in there. And so both of these are liquids, and so the milk doesn't dissolve in the water or anything, it just gets mixed in. And the milk then is the solute and the water is the solvent. And for most of the time, water is a solvent. But we could also have, what if you had 1 pound of table salt and you put that into 50 gallons of water? Some books will use the definition that the solute is the chemical that is being dissolved. So in this case, the sodium chloride is being dissolved, and the solvent is the chemical that does the dissolving. So there's two different definitions for that. Now we have a little thinker buddy here. Determine the solute and the solvent for each of the following. Okay, and so we could start off with beer. So if we're looking at the solvent, what do you think is the chemical present in the least amount, in the most amount? If you said water, you're correct. Now it would be the same for wine also, okay? It would be water. But what if we looked at something like air? So you have to look at all the different parts of air and figure out which one is present in the most amount. And hopefully you pick nitrogen, because it's about 75% of the atmosphere. Gatorade, I probably think it's probably going to be water. Guess what's seawater? Water. Okay. Now when we're talking about brass, brass is going to be a mixture that has copper in it and zinc in it. And so let's look at the color of brass. Now zinc is gray and copper is kind of an orangey yellow color. So if we're looking at brass, what do you think the solvent, quote unquote, is? I probably think it's the copper too, because the copper is more like the color of brass. 1 molar nickel 1 nitrate. Okay, so we're looking at NiNO3. Whenever we're talking about this molar thing, it's a concentration, and the solvent is water. Now, if we wanted to talk about solute, well, here with the nickel 1 nitrate, that would be the solute. Okay, in wine, you're going to have like grape juice, tannins, if you've ever heard about the great things of tannins inside wine. Beer will have things like hops, and you can have coloring, like down here. I don't think there is anything really blue in nature. We could have some sugar in there. We could have, some electrolytes, which they always talk about, and Gatorade, something like that. Now, when we talk about solutions, we really want to know about the concentration. And so it is always talking about the amount of solute versus the amount of solvent. The more solute, the more concentrated a solution will be. Now, one of the units of concentration that is really important is called molarity. Wow, look, it has the word mole in it. And molarity, by definition, is capital M, okay, is its abbreviation, and it is the moles of the solute, okay, and that's usually given by little n here for moles, divided by the liters of solution. So that's both the solvent and the solute together. And typically, obviously, the units of that will be in liters. So you'll see in the picture, if we wanted to make a solution, let's say we take 1 mole of copper chloride, and so we could figure out what mass that is using the periodic table. And we place the copper chloride into this instrument, this glassware, which is called a volumetric flask. And a volumetric flask has a line on the neck of it, and it only gives you one particular volume. This one probably is about 500 mils or so. Actually, this is 1 liter, sorry. A 1 liter volumetric flask. And so then what we do is we add water, okay, until it reaches this line. And whenever we're measuring in lab, and when you get into lab, you're going to see this, liquids tend to wick up the sides of glassware, and they form this upside down bubble called a meniscus. And we always read the bottom of the meniscus. And so we want to put distilled water until the bottom of the meniscus just reaches that line. And then, of course, we'll mix it. You'll see here in a blown up version our inverted bubble called our meniscus, and you'll see it lies on the line. And so then this is said to be a 1 molar solution then, and we always want to say of what solute we have. And so it is 1 molar. 1 mole of this stuff was dissolved in 1 liter. Now, if we pour out 1 liter of this solution, we have transferred 1 mole of copper chloride. And then we can figure out how many grams of copper chloride we actually poured out then. Because copper weighs 63, chlorine weighs around 35. Okay, so we're pouring out, in the form of a solution, roughly 98 grams of copper chloride. So we can use this, as a conversion factor, going from volume of solution into moles of something. Okay, and so I know you didn't want to hear that, but you're going to hear it. There are going to be problems that are associated with this mole. Now, what we want to look at is, first of all, just calculating molarity. So here we have 232 grams of potassium iodide, and it makes up a ½ liter of solution. What is the molarity? Well, by definition, you have to have moles per liter, okay? But we're not in moles. So we're going to take the 232 grams of Ki, and we're going to put that into liters. So let's start out with that. And so again, remember, it's for 1 mole of potassium iodide, and this is from the periodic table. And so those will cancel, grams of potassium iodide. Now we have moles. And then, once we have moles upstairs, all we have to do is divide it by the liters. And so here, if we have the volume in milliliters, let's convert it into liters. So milliliters cancel. And it's 1 over the volume, because moles will be divided by the volume. And so then we're going to get our final answer here, 2.795 moles per liter. And if we look at sig figs, there's 3 here, and there's 4 here. So there'll only be 3 in the answer. And so this will round to 2.80 molarity, and you must always say of what solute. If you don't, it's meaningless. Now, what mass of Ki is required to make 500 mils of 2.80 molar Ki? And you might say to yourself, what? You just asked me this question, lady. That's because I just asked it backwards. So you can start with this 500 mils. I wouldn't start with molarity because it has 2 units associated with it, and it's really hard to deal with. And so I would start with the 500 mils. I would say, all right, let's get rid of mils, and let's get that into liters. because I know liters are in molarity. So milliliters cancel, now I have liters. Now, whenever I see a problem that has molarity in it, and I'm not kidding you, I really actually do this, I always write down the units that are on there so I don't forget, because I can use this as a conversion factor. The liters cancel, then now I have moles of Ki, and yoo-hoo, you can get mass from that because you got moles, guys. And so we get the 232.4 grams, and with our 3 significant digits, 232 grams. So I can ask the question backwards if I choose to do that. So let's look at another problem here, hopefully, maybe. My mouse works. It says we dissolve 18 grams of lithium oxide in sufficient amount of water so that when it all dissolves, we get 500 mils of solution. Calculate the molarity. The same type of problem that we had before. We take our 18 grams of lithium oxide, and we can put the 500 mils on the bottom. Whoops, we forgot to put the 0.0 there for sig figs. We can convert, first of all, the grams into moles of lithium oxide. So let's do that. Now we have moles upstairs. All we have to do is get liters downstairs. So we've got milliliters there. Let's take 1,000 milliliters as a liter, and voila, we're going to get our answer. Okay, 1.20 molarity. Because there's 3 sig figs up here, 4 down there, because there were 4. So we'll only have 3 in our answer. Now, we can also ask an additional question. What is the molarity of lithium plus 1 ion? And you might say, what are you talking about, Heather? Well, remember, let's look at the formula. For every 1 mole of lithium oxide, that will be made up of, 2 moles of Li+, because there's 2 in here, and they're ions. It's also equal to 1 mole of the oxygen minus 2 ion, because the oxygen is in there also. Because remember, we went through formulas in the last chapter. We've got lithium plus going with the oxygen minus 2, and when we did our swap, drop, and reduce, that's how we got Li2O. So it is 2 moles of lithium. So let's use that as a conversion factor. We have this many moles of lithium oxide per liter, that's the molarity, and we just have to use this guy right here. For every 1 mole of lithium oxide solution we have, it has 2 moles of lithium plus 1 floating in it. And so these will cancel, and what you'll get here is 2.4 molar of the lithium plus 1, because 2 times 1.20 is the 2.40 molarity of the lithium plus 1 ion. Now, we can ask the question in multiple ways, and hello, I do that, and so you can't really memorize how to do these problems, and that's why I say chapter 4 is going to be really challenging. You guys can do it. I know you can. I did it, so anybody can do it. It just took me a long time to study this stuff. I had to do a lot of problems. In fact, I was one of those students that did all the problems in the back of the chapter because I didn't quite get it. I had to sit and practice and practice and practice. Now, there are some students that can read something one time and get it. I am not one of those students, and that's the truth. I'm not. I have to study a lot. Sometimes I have to look at something like 4 or 5 times before I get it. I'm a better student now than I was when I was a student, but I've learned some things along the way, like how to learn, how to study, what is my style. And so I like to listen and I like to watch stuff. So I like watching videos. I love YouTube, as you all saw. But I also have to do all the problems because it's not intuitive to me. So if you guys are struggling, go to the tutoring center or get online with the tutoring center, or of course use the Ask Answer discussion board, because as you see, I usually comment on everybody's posts. So I'm here to help you. So first of all, it talks about sodium chloride in blood serum. And It's true, we do have salt in our blood, and if we didn't, we would be dead. Okay, and so the molarity of the sodium chloride is 0.14 molarity. This is what volume of blood in milliliters contains 2.2 grams of sodium chloride. So you might say to yourself, what is she talking about here? First of all, do what I told you to do. Write down, if you've got molarity, what that really means. So it's 0.14 moles of sodium chloride. Now, the only other number they give us is 2.2 grams of sodium chloride. If I'm given a choice, I'm going to pick this number to start with first because it only has 1 unit on it. This thing has 2, and it's a pain to start with 2. So I'm going to start with the 2.2 grams of sodium chloride. Guess what? It's not in moles, guys. Let's get it into moles. So again, we'll use our periodic table, and we'll get this into moles, and our units will cancel. Now, once we have moles of sodium chloride, this goes from moles into volume, and we eventually want volume. So we're going to flip this upside down, and so 0.14 moles of the sodium chloride is a liter of solution. So the moles cancel, our grams cancel. Right now we have liters. How do you get it into milliliters? Well, geez, we did that back in chapter 1. And so if we do that, just our 1 liter is 1,000 milliliters, and then if we get that to cancel out, we're going to see that this is what our calculator comes out with. So we've got 3 sig figs here, 6 here, 2 here. So our answer can only have 2, okay? So that's a mistake there. I'm going to write that down in my book because we should only have 2. So 270 milliliters of the 0.14 molar sodium chloride solution. So see, sometimes I don't even look at my significant digits. So I need to be more careful about that too. All right. Oops, hold on. That was my alarm for jury duty. Yeah, that was fun. And so, if you've ever had to do that, interesting. I don't have jury duty tomorrow, but anyway. Whenever you have a solution, it may be very, very concentrated. And what I mean by that is there is a lot of solute in there per solvent. One thing that I can think of is when you go to the grocery store and buy orange juice in the frozen food section. The orange juice is very concentrated. And so when you open it up, it's like this big gooey slurry of orange juice. And you can't drink that, and don't try. You have to pour it into a container and then add water. And what you're doing is you're diluting it. You're adding more solvent, okay? And so now the concentration is going down. And so this process is called dilution. Now, when we are diluting something, okay, we're just adding solvent. So now there is just more volume, but the same number of moles of the solute. Now, what we'll see here is that the moles of solute before dilution must equal the moles of solute after dilution, because we didn't add any solute. The difference is, of course, the volume of the solvent. So there's a great equation that we use. C1V1 equals C2V2, or C initial, okay, V initial, what's the initial volume, the initial concentration, versus the final concentration and the final volume. So you'll see the equation either way. If you want, I would stick this on a note card. Now, when you're diluting a solution, what you may have is, let's say we have a 1 molar solution in this volumetric flask. And we're going to dilute it to a much larger volumetric flask. So we pour some of this, solution in, and then we just add more water. And so what we'll see is, of course, it's a lighter color because it's less concentrated. And we can figure out what the molarity of this new solution is using that equation. So let's look at a problem that addresses that. How would you make 60 mils of a 0.2 molar nitric acid solution from a stock solution that is 4 molar in nitric acid? Stock solutions are typically solutions that we buy. We put them in the stock room, we buy them at that concentration, and then we dilute them down for student use, and obviously different recipes call for different concentrations. And so we buy a concentrated solution and then we can dilute it down instead of buying every concentration of solution from the chemical companies. They would love us to do that, but we just don't have that kind of money. So what we want to do is, of course, use the dilution equation. And the reason why I want to is they have two different concentrations of the same chemical. So I know I'm going to have to use this equation because it has two different concentrations. So let's first of all look at C1. What is the initial concentration? Well, it's 4 molarity, okay? What is the new concentration? Well, we want it to be 0.2 molarity. And it says, what is the new volume? Because it says we want it to be eventually 60 mils. So all I did was convert this into liters, okay? And then what was the original volume? So what I'm asking here is, let's go back. What is this original volume? I'm pouring it in here, and I'm getting this up eventually to 60 mils, okay? And this is now 0.200 molarity. This stuff was 4.00 molarity in my equation. So it's saying you're going to add water. What is the amount here that we poured into the original, into this bigger, container? So let's move forward. So all I did was rearrange algebraically this equation to solve for V1. I plug all my numbers in, so I have molarity here, and liters here. So molarity cancels, and you'll see all I have left is liters. So it's 0.003 liters or 3.00 milliliters, because there are 3 significant digits, 3 here, and there was 3 here. So we'll have 3 in our answer. And so we would take 3.00 milliliters of the 4.00 molar nitric acid. Now, how we would prepare that is we would take 3 mils of the acid, we'd add roughly 57 mils of water, so we get it up to the 60 mil line, and boom, we have 60 mils now of this new concentration. Well, let's look at it again. You need to make 135 liters of a 0.1 molar saline drip solution. Could you make enough starting with 0.0023 kiloliters, okay, of 6 molar solution? Now, first of all, what is the initial concentration? Okay, so it's 6 molarity. What is the new concentration? 0.1 molarity. What's the initial volume? Well, I'm going to take this 0.0023 kiloliters, and it actually is 2.30 liters then. If you don't believe me, do the conversion, and we want the new volume. And so rearranging our equation, the molarity cancels, we're stuck with liters, and so 138 liters of 0.100 molar solution. Now I wanted to make 135 liters, and this stuff makes this amount of saline. So yes, I can actually make this amount. I can make 138, and I only needed 135. Now, molarity is then a conversion factor. So you'll see here we can go from moles of one chemical to volume, or from volume to moles. And then if we wanted to go from moles of chemical A to chemical B, you guys know you have to use a mole to mole conversion factor. And then if you wanted to go from moles of chemical B to its volume, use molarity. So let's look at an example. What volume of 2.5 molar HCl, and I want that volume in liters, is required to convert 11.8 grams of zinc completely to its products? So this one, when you're looking at it, you're like, I don't even know where to start, lady. Remember molarity? Let's just write it down. It's our conversion factor. So this is going to get me my answer in liters because my answer has to be in liters. This has liters. I need to use this conversion factor, and that is HCl. Just kind of ran out of room there. This has only got 1 unit attributed to it, so I'm going to start with this. 11.8 grams of zinc. It's not in moles, guys. Get it into moles. So grams of zinc cancel, and now I'm in moles. Now we're looking at zinc and HCl, so we need to look at these two chemicals, so you need a mole-to-mole conversion. So now we're going to do for every 1 mole of zinc in the balanced equation, it will require 2 moles of HCl. So moles of zinc cancel, now you have moles of HCl, and we want volume of HCl. Guess what? This has moles of HCl and volume. So let's flip it upside down so that the moles is in the basement, and now we have liters. So our answer will be 0.144 liters of HCl. Yippee! It's a conversion factor. Please do not forget that. Students a lot of the times forget this is a conversion factor, and yes, you will do problems like this. All right, that's it then for section 4.4.